So a few topics I wanted to cover with you are parallel file system metadata and some of the issues that we see as that becomes more and more of a concern for users as the metadata workloads grow. I think in order to sort of understand that, it would be useful to talk about a Lustre parallel file system, kind of present an overview. Most people are familiar with it, not all are. I wanted to talk a little bit about that. Talk about metadata and the concept of a distributed namespace within Lustre and how that works. And then I'm actually a performance engineer who does benchmarking for the majority of my time. So I'm going to talk about a few metadata tests that I've been able to put together and like to share those performance results with you, both for scaling the number of metadata servers to be able to increase and handle increasing metadata workload, and also the performance of high availability when you have a case where you fail over one node to another, that behavior. So typically, when we think of parallel file system performance, everybody talks about gigabytes per second, what's your throughput, what's the bandwidth. And so that's been a problem that has been worked on for many years now. And to some extent, it's largely addressed. But then sort of what becomes the next problem that people are beginning to look at. And we see much more with metadata. Metadata being the data that describes files, whether it's the access allowed permissions for that file, or the size of the file, or information about it. And with increasing number of files that we see, that becomes more of a problem. And we see this in many areas, but specifically we see this with genomic data processing, large number of files. CPU chip manufacturing actually will use significant numbers of files that they're working on. One of the ones that's actually kind of interesting is in video. When you're compositing and rendering, for example, you're rendering a film, you have 24 frames per second. Each one of those frames is a file, and you figure, well, whatever your movie is 2 hours long, 24 files per second for that length of time, maybe 200,000 files. Doesn't seem like that many necessarily. It's not trivial, but in point of fact, each one of those frames that's generated, you might have tens, sometimes even as many as 100 separate files in the process of rendering that to be the single frame. So you can start to very, very quickly add up large numbers of files. So metadata becomes more and more of an issue that people are beginning to focus on. So with that in mind, I'm going to jump into Lustre, the parallel file system, and it's sort of its design. So Lustre is an open source, distributed, object-based parallel file system. And by object-based, I mean that communication between the clients and, let's see if I can get this right, and our storage servers, and you can have a large array of storage servers, you're able to pass the data across the network to the storage servers, handing off large streams of data to an object on the storage servers, which is going to be different than a block-based storage system. And what that allows you to do is have communication directly between these clients and these storage servers, bypassing sort of a middleman, a metadata server, for example, and you can get outstanding bandwidth performance by doing this. And that's been sort of the big focus for a long time with these parallel-based file systems. How do I increase my bandwidth? Well, let's see. If I can get this metadata server out of my way so that I can have my clients talk directly to my storage servers in parallel, and I don't have a bottleneck, I'll be able to get really, really good bandwidth performance. And that's great. That's what we want to see. But there's sort of more to it than that, right? The file system is comprised of the clients, comprised of storage servers, and behind each one of these storage servers is an array of disks, which we'll call an object storage target. But there's also this metadata server, and you sort of getting short shrift, right? Traditionally, you have one or two as an active-passive arrangement with the metadata server. And this metadata server also has a metadata target behind him. But what if you were able to have multiple metadata servers so that you're able to scale your metadata workload as well as your bandwidth I/O workload. So the concept is to have really, to address that problem with the metadata, is to have a distributed namespace. So your namespace being all of the space available for your file names as that grows, but you want to be able to distribute that so it's not anchored just to one metadata server. And so that was the concept of the distributed namespace, DNE, and I'll just refer to it DNE henceforth, that came about in Lustre 2.5. That would allow you to have multiple metadata servers rather than just one metadata server with a passive and a failover arrangement. And then you could divide your entire namespace, all the names of your files, across multiple metadata servers. And by doing so, you could scale your metadata performance. And so that was the intent for the distributed namespace effort with Lustre. And that was comprised of two phases. The first phase was in Lustre 2.5 release, and that was to be able to have remote directories. So you'd have your main metadata server here. We're going to keep the root on him, but we can also have additional metadata servers. We'll call them DNEs, but they're just metadata servers that are remote to this main root metadata server. And each one of these can be, in this case, a failover pair. So this is think of these as a box of two metadata servers. And so they're a failover pair unto themselves, as are these. And as you increase the metadata workload, you can partition the namespace so that you have directory B on this guy and directory E on this guy, so that you're able to take advantage of increasing metadata servers. So that's sort of the first phase with DNE for Lustre. The second phase would be to actually stripe the directory so that you would be able to have one directory as he became a hotspot and he had a huge metadata workload on him, would be able to be distributed across the various metadata servers. This would have performance advantages for that one particular directory. And actually there's sort of plans for a phase 3 to even enhance upon that and have that be dynamic. But I'm not going to get into that. But you actually be able to dynamically distribute that workload if you're able to develop hotspots in specific directories. So sort of with that in mind, now I'm going to jump back and talk about how there is an engineered storage solution from Seagate called Clusterstore that integrates Lustre, what we just talked about, onto the Seagate hardware. And to do that, there has to be a fair amount of architecture involved, make sure that we actually have an integration between the Lustre parallel file system, this open source file system, because you could just run that on anything, but it might not behave quite the way you want it to. If you're actually going to integrate it with the hardware from Seagate, you're going to have to optimize it, make sure that it behaves correctly and performs well, a series of qualifications, and make sure that this is supported. And the reason is because there's so many pieces on this layer cake that are involved, right? You have to integrate with the high-speed network, then the actual Lustre parallel file system is, in point of fact, sort of a smaller piece even of it, all the way down to the storage disks themselves. And so there's this overall structure that needs to be maintained for the system to work seamlessly and flawlessly. And so one of the things that we also provide with that is a Clusterstore manager. This can either be through a command line interface or through a GUI. With the GUI, you have the opportunity to be able to see your bandwidth or your metadata load at any given moment, and you can see various, if there's an issue on the system, you need to address that, look at that. So this is a fully integrated solution, right? So jumping back to the components of Lustre, there's really, it sort of boils down to 3 different pieces for the parallel file system, right? There's going to be a client piece, which is just going to be a set of software RPMs that are running on your client. There is also the metadata server or metadata servers that we just talked about. And so the clients will be talking to the metadata server and getting various file permissions and being able to open and close a file, maintain a certain state so that it recognizes that there's concurrent access to the file. And then there's also the third piece, the object storage servers. That's actually where the data resides. Metadata will reside here. Storage data, what you actually think of your data in your file, will reside on the object storage servers. And so the metadata server will contact these object storage servers for file creation, to actually allocate the space on the storage target, make sure that there's no issue going on, is the system in recovery. And the last piece then being between the clients talking directly to the object storage servers. And remember, behind each one of these guys is an array of disks for the object storage server and also for the metadata server. So the next thing I'm going to look at is the metadata server and how we're implementing that in the Clusterstore product. And then we'll take a look also at the storage server. So we call it a CMU, which is the Clusterstore Management Unit, and that will include the 2 nodes that are doing management. So this is a 2U 4-node server, Sandy Bridge servers, and the first 2, and so this is a little picture of it, right? These first 2 top nodes here are actually just going to be doing management of the entire Clusterstore, not management necessarily of Lustre unto itself, but just for the Clusterstore, and they each have a little disk on them that you boot from them initially. Beneath them are 2 other servers that are also in a failover pair. One's called the MGS, which is the Lustre Management Server. It runs processes managing all of Lustre. It's a little different than the Clusterstore management. And also one node here, which is our MDS. So earlier we were talking about the MDS. Well, actually here we get to see this guy. And he's in a failover pair with the MGS, the guy next to him. He fails. The other guy picks up in a fault tolerance arrangement, picks up the metadata workload for him. Behind that, so that's just the server. Behind that is an array of disks. And so this array of disks actually, I believe it ends up being a grand total of 24. Yeah, the 2U box with 24 disks. And we partition these so that 4 of these disks are actually maintaining Lustre management. 4 of these are on the Clusterstore management, again, sort of a different system managing. Then we have the hot spares, and then actually 14 drives are for the metadata target. So the other piece was the object storage server. With the object storage server, this is a 5U box that contains 84 drives. So we refer to it as a 5U84 or an SSU, or a scalable storage unit. That's just how we describe the object storage server. And what that really is, I'm going to look at the back of the box for just a moment, is it's 2 storage servers, and each one of these storage servers is talking to a tray of 42 disks. So the top one's 42 and the bottom one's 42. And this is in a failover arrangement as well. So that each one has an affinity, these servers, to an array of 42 disks. But should one of these servers fail over, the other one can see all 84 in grand total. Granted, your performance will be half that during that phase until it has been reconnected and configured. For the connectivity for this can either be InfiniBand, QDR, FDR, or as well 40 gig Ethernet. But what we looked at only included a single metadata server. What we're interested in is to be able to expand on our metadata workload, have multiple metadata servers. And so with Clusterstore, our new release that's coming out very soon, actually we're starting to deploy it right now, will have Lustre 2.5, and therefore it'll have the capability to have a distributed namespace. And so how we're implementing that is in a pair of 2U servers. Each one will be running a metadata server. And this is actually active-active. This is not an active-passive that we looked at in the previous slide on the metadata, the sort of the primary metadata server. And with this, we can build on this primary metadata server for a certain metadata workload, and as we add more and more metadata servers, the DNEs, we can improve the performance and scale the metadata performance. So let's take a look really briefly on how this is happening from the communication between the client and the Clusterstore. Clusterstore wants to talk to one of the files. However, the client wants to talk to Clusterstore to find access to one of these files or generate a file. So the first thing the client does is it contacts the primary metadata server and says, I'm looking for this file. Here's the path name. The metadata server may have that path name as it's part of its domain, its namespace. If not, it will recognize where that is and report back to the client saying it's actually on this metadata server over here, which therefore will be cached by the client henceforth, so it doesn't have to keep making communication to the primary metadata server. But let's just assume it's on this primary metadata server. Primary metadata server will respond to the client saying, yeah, your file is located on these various storage servers. The client henceforth will not be communicating with the metadata server. It'll be going directly with its file. In this case, we just arbitrarily picked a 3 megabyte file, not particularly large, to the storage server. And the file can be fanned across multiple storage servers. In this case, we'd be putting 1 meg on each one of these 3 storage servers. And behind that, the object storage target, the actual disks where the data reside, we would be writing, the storage servers would be writing out their 1 meg stripe of the full file, and 1 meg stripe, 1 meg stripe. Or this could be a read operation, but now it knows the location from the metadata server of the files, components, and it will know how to contact the various storage servers to get these pieces of the file or write to these pieces of the file. So putting on my benchmark hat, it was just too tempting not to run some tests to be able to determine how much speed up are you really seeing as you add more and more DNE servers. And so the test I ran was with a single primary MDS and then 4 DNE servers. So 4 of these separate servers. We actually refer to a pair of these servers as an ADU, an additional DNE unit. I didn't want to get too much into all that kind of terminology, but if you're wondering what that was referring to. But what we're really interested in, I have my primary metadata server, and as I add additional DNE servers, how is that going to scale? And so the test that we used is called MD test. This is probably one of the sort of standard industry benchmarks for metadata workloads. It does a couple of things. It creates a whole bunch of files. It stats a bunch of files. It can actually read files. That's been added to it. But mostly we're interested in the last piece, deleting files. And so with a create, and so I'm going to look at these numbers here with the average create of 5 runs. On a single metadata server, we're seeing about 70,000 creates a second for the sort of baseline metadata server. As we add the first DNE, we go from 70,000 to maybe 100,000. Add the next guy, so this is 2 metadata server, additional DNE servers. And you continue to rise to, I think we got to about 160, 170,000 creates a second. Now this is 0-length files. This is trying to push the metadata as hard as you possibly can to demonstrate what is possible. As well, ran some a stat workload doing this. Now the stat is much, much faster here. And the reason for that is really the stat is primarily just doing a simple read operation of the metadata, whereas with the create, you actually are going to have to allocate some space on the object storage targets. You're going to have to write the data on the metadata. You have to write the metadata on the MDS or on the DNE. And so the stats we're seeing a little over 300,000 climbing to about 500,000 stats a second with increasing DNE servers. And then finally, we also ran that with the delete workload just to get rid of all the millions and millions of files we generated here. And remove or unlink really is sort of on par with a create. That's because you actually have to not only just do a read, but you have to do an update of that, release that inode and the pre-created object on the object storage servers. So the other test that I wanted to do was to understand the behavior of the high availability. So with the high availability with the pair of D&E servers, each one of these guys is active. Each pair is active. And so if one of them fails over, am I able to pick up the workload from the other one? I don't expect it to be as fast as when both are running, but I expect it to be no less than half that speed. And can it handle that? And so that was the test that I was running here with the a pair of D&Es, the ADU that I mentioned before. So this is before a failover. I was seeing for this particular one, I remember this was just 2 D&Es. This didn't involve the primary metadata server. We're seeing close to 40,000 creates a second. Then I manually failed this guy over. I could have just rebooted him, I suppose. But manually failed one of the metadata servers over, and the performance is just about half what I'd expect. And that was actually pretty seamless to be able to do that. That happens in real environments. Sometimes the server goes down. Be able to have that high availability failover and still maintain your expected metadata performance during that failover was great to see, particularly when we actually failed that server, brought them back online, and the performance went back up to what we were expecting to see, same as before. So the other thing that I wanted to mention today, it's a little bit of an abrupt change. I wanted to mention something that I find particularly interesting, a little bit different than the benchmarking and the metadata workloads that I was talking about, but something from Seagate called the Green Machine. And the Green Machine really has the objective of being, well, green, right? It wants to reduce the amount of space that it is using so that you're not using as much space on the machine room floor, reduce their cooling requirements, and corresponding with that is also the power requirements. So if you can get to a point where you have very little heat emission, I don't know, quite about 0, but that's what we're targeting here for heat emission from the system, reducing the number of fans that are necessary, and also allow the hard drives to be able to operate at a slightly higher temperature because you've removed various ambient cooling, various cooling fans. And then also correspondingly be able to reduce the power consumption of the system so that you're able to use low power servers. You know, there would be certain gains from that. And in addition, to be able to have a truly green system where you could recycle, you know, the chassis someday upon retirement, also reduce the overall amount of metal and you know, parts to the system. In this case also, as an installation, be responsible for disposing of the old chassis. So some of the areas that you might see something like the Green Machine, which is, when I've looked at the roadmap, is coming out later this year, would be for retrieval of content in deep storage, cold storage. And you want to be able to have, you know, whether it's your favorite social media site or whether, you know, it's you know, your collection of pictures from past vacations. You want to be able to have this maintained, but you don't want these disks necessarily spinning up all the time, wasting a lot of energy, but you want them available when you want it without using a lot of power and cooling and et cetera, what we talked about. And so that's really the objective rather of the Green Machine, as well, you know, other things that you'd want to retrieve, you know, your X-rays, your MRIs, stuff that you don't normally need access to, but when you do, you want to be able to spin up the disks and gain access to those. So that was what I wanted to cover today. If there was any questions.